In this video, we're going to talk about critical points. If f prime of x goes from positive to 0 to negative, then there is a local maximum at the point where f prime of x is equal to 0. So that could look something like this. We've got a positive first derivative, and then we've got a 0 first derivative, and then we've got a negative first derivative. Well, we can see that there's a local maximum there. And if f prime of x goes from positive to undefined to negative, and if f of x is defined at the point where f prime of x is undefined, then there's a local maximum at that point. This is our introduction to the idea of a cusp. You can have a function where the first derivative is positive. Then there's a point, and the point exists, but the first derivative is actually undefined there. We wouldn't know exactly where to draw that tangent line, would we? And then afterwards, the first derivative is negative. Well, there's a local maximum at that point as well. And perhaps those are better diagrams. Similarly, the first derivative test continues, and we can say that f prime of x can go from negative to 0 to positive. And if that happens, then at the point where f prime of x is 0, we'll call that a local minimum. And similarly, the same thing can happen with the presence of a cusp. If there's a point at which f of x is defined, but f prime of x is undefined, but we're going from a negative slope to an undefined slope to a positive slope, then we can say there's going to be a local minimum there. And that's what that graph would look like. So in both of these last couple of examples, we call those weirder looking curves that perhaps we're not used to. We call those cusps, those points. Now, another situation can occur when we have a first derivative that's positive, and then it's 0, and then it's positive again. An example of this is y equals x squared. There's a point there with a horizontal tangent line, and we've gone from a positive to a 0 to a positive. Well, at the point where f prime of x is equal to 0, at the point with the 0 first derivative, that's neither a maximum nor a minimum. And similarly, we can have a point with we can have a curve that has a negative first derivative and then a 0 first derivative and then a negative. And an example of this is y equals negative x cubed. And that'll have a, like we see, negatively sloped tangent line and then a 0 slope tangent line and then a negatively sloped tangent line. And that point with the 0 tangent, that is neither maximum nor minimum. Okay. So let's now talk about what a critical point, critical number are. The points at which f of x is defined, but f prime x is equal to 0 or f prime x is undefined are called critical points. And to find the critical points, we first find the critical numbers, which are the x values at which we have a critical point. Okay. So, for example, suppose we're given the function y equals x to the 4 minus 8x cubed plus 18x squared. We want to determine all the critical points. And then we want to determine whether each one of those critical points represents a local max, a local min, or neither. So we can begin by determining the derivative of that fourth degree polynomial, which is this third degree polynomial right there. We're then going to factor that. And after common factoring and then trinomial factoring, we get 4x, x minus 3 quantity squared is equal to the first derivative. Now, we want to set that first derivative equal to 0. So if we say 0 is equal to 4x times x minus 3 quantity squared, then that means either x is 0 or x is 3. So we create ourselves a number line, which we've done here, where we have a 0 and a 3 delineated on that number line. Now what we're going to do is we're going to take a representative number to the left of 0. It could be any number, so let's say negative 1. If we plug -1 in for x and calculate calculate f prime of x, which is 4x times x minus 3 quantity squared, we will get a negative value. If we then choose an x value in between 0 and 3, for instance, let x equal 1, and then we calculate 4x times x minus 3 quantity squared, we'll get a positive number. And if we pick a number greater than 3 and plug that in for x and evaluate f prime at x, we'll get a positive number here as well. Well, what this means is we have a negative first derivative, a 0 first derivative, and a positive first derivative. Our curve's going to look something like this. And then here we've got a positive first derivative and a 0 first derivative and a positive first derivative. Well, our curve's going to look something like this. That point there is neither a local max nor a local min, but this point down at the bottom, that is a local min. Okay, and that's the first derivative test in action. So we can say, therefore, the critical numbers are at x equals 0 and x equals 3. Those were the values of x that set the first derivative equal to 0. Now, the critical number at x equals 0 is a local minimum. We expressed that on the previous slide. And at x equals 3, it's neither. Well, those are critical numbers, but what are the critical points? Well, that's pretty easy to figure out. We just take those x values and sub them into the original expression for y. At x equals 0, y is 0, so the point is 0, 0. And at x equals 3, y is 27, so the point is 3, 27. We've got two critical points. The first one is a local minimum, and the second one is neither a local minimum nor a local maximum. Now, in this one, we want to determine whether the function f of x equals x cubed has a maximum, a minimum, or neither at the point where f prime at c equals 0. So all we're going to do is we're going to determine the first derivative here, which is 3x squared, and we're going to set it equal to 0. When we do that, we solve for x, we get x is equal to 0. Okay, so we've got one critical number. We're then going to build a number line, which we do. And we now are going to take a x value to the left of 0 and plug it into f prime at x and see if we get a positive or negative value. We get a positive value. Now we're going to take a number to the right of 0 and plug it in for x and see if f prime at x is positive or negative, and we'll again see that it's a positive value. So what we've got is a point where we've got a curve with a positive first derivative, a 0 first derivative, and then another positive first derivative. We're going to have neither a maximum nor a minimum there. So the critical number x equals 0 represents neither a max nor a min. We'd like to know the critical point though, and that part's easy. We actually just at x equals 0, evaluate what y would be. We sub it into the original expression of x cubed. 0 cubed is 0, so the point itself is 0, 0. So what we've now found is that the critical point of 0, 0 is neither a maximum nor a minimum. In our next example, we're going to determine critical numbers for the function shown and then determine whether each one is a local max, a local min, or neither. So the function square root of that quadratic will be re-expressed as that quadratic raised to the exponent of 1/2. And then when we determine the derivative, we get this expression here using the chain rule. We then just sort of re-express this expression this way. And then when we factor the 2 from the numerator and denominator and cross it out, we ultimately get that the first derivative is equal to x minus 2 over the square root of a quadratic. Well, we want to determine where the first derivative can be 0. So what we're going to do, we've got our first derivative equal to x minus 2 over the square root of x squared minus 4x plus 8. This happens quite frequently in these type of examples. We're going to actually let the numerator of the first derivative equal to 0. So if I let the first derivative itself equal to 0, then multiplying both sides by the denominator means essentially I'm just saying x minus 2 is equal to 0. Solving for x is pretty simple, and that's what we've written down here. We have x is equal to 2. That's the x value that makes the first derivative equal to 0. Now, the x value that makes the first derivative undefined will be whatever x value makes the square root of that quadratic equal to 0, whatever makes the denominator 0. Well, if the square root of x squared minus 4x plus 8 is equal to 0, then squaring both sides means x squared minus 4x plus 8 itself is equal to 0. So let's solve for x. When we use the quadratic formula there, we ultimately get a value for x, which is 4 plus or minus the square root of negative 16 all over 2. But we can't take a square root of a negative. So there are no values for x for which the denominator is equal to 0. So there's no values of x for which y prime is undefined. So what that means is the only value for x that makes the first derivative either 0 or undefined is x equals 2. Okay. Now, we're going to set up our intervals for interval testing. I make a note here that the denominator is actually never negative. The square root of x squared minus 4x plus 8 cannot be negative no matter what value you plug in. But even if a person didn't quite recognize that, they could still do the interval testing. Simply take a value to the left of 2, for instance, let x equal 1, or any value you want to the left of 2. And if you sub that in and evaluate y prime, you will get a negative number. Now, take any x value to the right of 2, for instance, 3, and plug that in for x. And if you evaluate this value right here, you'll see that the y prime is positive. So what we know is that our curve has a negative first derivative and then a 0 first derivative and then a positive first derivative. So we're talking about a minimum point there. Okay. Now, the critical number is x equals 2. What's the critical point? Well, that's actually the easiest part probably. Just take that x value and sub it in for the original expression for y. Ultimately, that means y will equal 2. So at the x value of 2, y is equal to 2. We've determined it to be a minimum. So that means the critical point 2 is a minimum, local minimum. Now, for this next question, we're going to determine critical numbers for the function shown, y equals x plus 3 quantity to the 1/3, and determine whether each critical number is a maximum, a minimum, or neither. So to determine the derivative of that, we're going to need the chain rule. And so doing a pretty straightforward chain rule opportunity, we have 1 over 3 times the quantity x plus 3 to the 2/3. And I like to express that as x plus 3 quantity to the 1/3 and then make that quantity squared. I don't always trust calculators to do a good job evaluating something to the exponent 2/3. So I like to just think in my own mind, what is that base raised to the 1/3, and then I square it. If I do it that way, I don't get mistakes with signs, whether it's positive or negative. If I rely on the calculator and my ability to enter in brackets appropriately at each step, I tend to make mistakes that way. So I would really strongly urge you just to think about when it comes to the sign, positive or negative, ask yourself what's the sign of the third root of a particular value, and then square that and ask yourself what the sign of that will be. So anyways, got off track there, but coming back here, what I would say is that this first derivative right here, that first derivative can never equal 0, because if 1 over 3 times x plus 3 quantity to the 1/3 and then quantity squared, if that whole expression was to equal 0, then multiplying both sides by the denominator would mean 1 is equal to 0, and that can't happen. So clearly the denominator never, clearly y prime never equals 0, this part right here. Y prime never equals 0. But I can set that denominator equal to 0. So now this is the first part. Setting the denominator equal to 0 will help me find where that first derivative is undefined, because at any point where the denominator equals 0 is undefined. So this first derivative's denominator equaling 0, All I have to do there is divide both sides by 3, and then square root both sides, cube both sides, however you think about doing it. What you end up with is that x equaling -3 will make the base of that exponent 0. Therefore, x equaling -3 will make the first derivative undefined, so there is a critical number at x equals -3. And again, there's no critical numbers that stem from y prime equaling 0. So our only critical number is x equals -3. So we come back here, and now what we're going to do is we're going to determine whether that x value of -3 represents a maximum, a minimum, or neither. So how we do that is we pick a number to the left of -3. Let's say we take the number -4. If I let x be -4, then x plus 3 is a negative quantity. The third root of that will also be negative, but squaring that will make it positive. So I'll have 1 over 3 times a positive quantity, and that'll be positive. Now, similarly, I can let x be a number to the right of -3, any number I want, say, for instance, 100. If I let x be 100, then 103 raised to the exponent 1/3 is a positive number. Square that, I get a positive number. So my first derivative will be 1 over 3 times a positive value, and that will also be positive. So what I see is that I've got a situation where my first derivative is positive, and then it's undefined, and then it's positive. Well, that's going to be neither a maximum nor a minimum. So the critical number of x equaling -3 leads to neither a maximum nor a minimum. So let's figure out what the y value is at that point. Well, if you recall, the original function was x plus 3 quantity to the 1/3. Letting x equal -3 means our interior of the bracket is 0. 0 to the 1/3 is 0. So the critical point is -3, 0, and it's neither a maximum nor a minimum. Just in case you're curious, what might that look like? It actually, in that case, will look like this. We'll have a positive first derivative, an undefined first derivative, and a positive first derivative. We'll talk about that in a later video. Now you might be wondering, how can you call that an undefined first derivative when you can draw the tangent line? Well, the reason is the tangent line there is vertical and the slope of a vertical line is undefined. Now, let's do another example. Looks pretty similar to the second one, but it's going to have a different result. We're going to say y is equal to x plus 3 quantity to the 2/3, and we're going to see whether that critical number represents a max or a min or neither. So when we determine the derivative there, we've got 2/3 times x plus 3 quantity to the -1/3, and we reorder it a little bit, and we get 2 over 3 times x plus 3 quantity to the 1/3. Now, for the same reason as the last question, we cannot let that numerator equal 0 because it's impossible for 2 to equal 0. So there's not going to be any point at which our first derivative equals 0. But there might be a point at which the denominator of our first derivative equals 0. In other words, there might be an x value at which the first derivative is undefined. So if we let the numerator equal 0, we get ultimately x plus 3 equal to 0, which means ultimately that x is equal to -3. So the denominator equaling 0 means x equals -3. The only critical number, for reasons said earlier, is x equals -3. And so now what we can do is pick any number to the left of -3 and sub it back into the first derivative. We're doing interval testing on the first derivative. Well, if we let x be the number -4, then the interior of this bracket is negative. The third root of a negative number is negative. 3 times a negative is negative. So we would have 2 over a negative value, which is definitely negative. So to the left of -3, our first derivative will be negative. How about to the right of -3? Well, if I take a number like, again, any number to the right of -3 will do. Let's say we take the number 100. If I plug the number 100 in for x, then I'm taking the third root of 103. That's a positive value. Multiplied by 3 is still positive. So in that case, my first derivative will be 2 over a positive value, which will also be positive. So this is a value at which I'm going to have this is a critical number that is representing a minimum, because I have a negative first derivative, an undefined first derivative, and then a positive first derivative. Well, it'd be good to know what's the y coordinate of that. In order to figure that out, I simply plug -3 into the original expression, plug that in for x, and I'll get that a y coordinate equal to 0. So the only critical point will be the point -3, 0, which is a minimum. And if you're curious what that looks like, at the point -3, 0, we'll actually have a cusp. That's not a very well drawn cusp, but it'll look something like what's drawn up at the top of your page. Okay? Now for this question, they want to know values of a, b, and c such that f of x equals ax squared plus bx plus c has a local maximum of 5, 6, and passes through 8, -12. Well, this is a smooth polynomial curve, so I know that if there's a local maximum there, it'll be at a point where f prime x equals 0. So since that point is at an x value of 5, I can say f prime at 5 equals 0. Well, let's figure out the derivative of that polynomial function. The derivative is 2ax plus b. If I know that f prime 5 equals 0, then that's like saying 2a times 5 plus b is equal to 0, which means 10a plus b equals 0. Doing a pretty simple solving for b, I get b is equal to -10a. Well, I also know that the curve goes through 5, 6, and 8, -12. So that means f of 5 is 6 and f at 8 is -12. So if I simply let f at 5 equal 6, then what I get, as shown in this line here, is that 25a plus 5b plus c is equal to 6. And if I let f of 8 equal -12, then what I get is 64a plus 8b plus c is equal to -12. So plugging in our expression, we know from earlier that b must be equal to -10a. If I plug that into equation 2, I end up with c equaling 25a plus 6. And again, knowing that b must equal -10a, if I plug that into equation 3, I get c must equal 16a minus 12. Well, if c is equal to 25a plus 6 and c is equal to 16a minus 12, then it must be the case that 25a plus 6 equals 16a minus 12. In other words, ultimately, a is -2. Well, we know b is -10a, so b must be 20. And then go back to either equation 2 or equation 3. In equation 2, we saw 25a plus 5b plus c equals 6. Ultimately, that would mean c must be equal to -44 after plugging those values in for a and b. And so we get a final answer for this particular question, which is that a must be -2, b must be 20, and c must be -44. Now for this last question, what we're going to do is graph the curve y equals f prime x given this original function. So what we want to do is say to ourselves, is there any points on this curve where it's pretty easy for us to determine what the derivative actually equals to? And I would say yes. That point right there and that point right there, they pretty clearly to me have derivatives equal to 0. So at those x values, I'm going to let y equal 0 because they're telling me let y be the value of the derivative. So at the 1x value here, I've got a y value of 0 since the function has a horizontal tangent. And at the other value shown a little farther over to the left, I've also got a intercept because I've got a horizontal first derivative. Now, a horizontal tangent. Now, in between those two values, I see that I've got a negative slope all the way. Well, they're saying to me, make sure that your y coordinate is equal to that slope. So they're basically telling me, make sure I've got some negative y values in between. And I can draw those. And it even kind of makes sense because at first, this first derivative won't be too negative. But then as I go a little further down the line, I'm going to have a steeper slope, so a number that a greater magnitude, still negative. And then as I get a little bit closer to this x value, my slope of my tangent will still be negative, but not quite as much. So you can see that this pattern here, the bottom part of that parabola, is kind of mimicking the slope of this curve here. Now, after that, we're going to have positive first derivatives, which means the curve that we're asked to draw, which is y equals f prime of x, needs to have positive y values. And the same thing will happen over here. And then finally, we can take a step back and ask ourselves, does it make sense what we drew? And the short answer is yes. We were given what definitely appears to be a cubic polynomial function. So a third degree polynomial function. And then we were asked to graph the derivative of that. Well, the derivative of that, a third degree, using the power rule, is going to be second degree. And so I'm expecting to draw a parabola, and that is what we've in fact drawn. So the way we've described it on this PowerPoint is any point where f of x has a minimum or maximum, that's where f prime of x equals 0, so that means y equals f prime of x will have an x-intercept there, so I indicate those two with the red slashes on the left. Then over any intervals where y equals f of x is decreasing, that means f prime of x is negative, so the curve of y equals f prime of x should be below the x-axis. That's what's drawn there. And then any intervals where y equals f of x is decreasing, f prime of x is negative, so the curve will be below the x-axis. And since y equals f of x is cubic, y equals f prime of x should be quadratic, and that's what we've drawn.